So here a uniform semicircular wire or a ring is hinged at point A so that it can rotate freely in a vertical plane about the horizontal axis through A. So this is A where the hinge is. Now when it is released, this diagram is shown. That means the diameter AB is horizontal. Find the hinge force A immediately after the wire is released. So immediately after the wire is released, that wire is still at rest, so the angular velocity is 0 just after the wire is released. With time it will when the wire falls, then it will gain angular speed, but just at the time of release it will have 0 angular speed. So first, there is a fixed axis, so we can apply torque equation about the hinge. So this is the center of mass C. Now the distance of the center of mass here is 2r by pi, and this is obviously r. So the weight acts downwards. Weight is acting downward, mg. So we will apply the torque equation from hinge. Torque equation from hinge will give you mg multiplied by r is equal to I about a times alpha. Alpha is angular acceleration, which is in this clockwise sense, obviously. So what is I about a? So let's take that for suppose you with this half ring you include one more half ring, so that the total mass becomes 2m rather, and about an axis through the end a, moment of inertia. Say for each half ring it is Ia, so this becomes twice Ia is equal to, now we can apply parallel axis theorem from the center to this point. So the distance between the axes is r, so twice Ia is equal to 2m times r square. Now it's a ring of mass 2m plus 2m times mass times d square, so d is also r, so that becomes 4m times r square. So Ia becomes 2m times r square. So therefore in the torque equation we can write mg into r is equal to 2m r squared times alpha, implies alpha is equal to g divided by 2r. Okay, so now we have to apply the force equation. Before finding the force equation from A to R, so with respect to A, C is in circular path, so C should have a centripetal acceleration and a tangential acceleration as well, but the centripetal acceleration is 0 because r omega square. So let this be r, this r is equal to distance from AC, so r omega square sorry, which is towards A, so that part is 0. It is only having tangential acceleration because the system is just released, so it's still at rest. So this acceleration is not there, only you have the tangential acceleration, which is r alpha. Now let that be theta, this is also theta. So what are the components? So this is r alpha cos theta, and this is r alpha sin theta. Now so we have the system A. Here the hinge force we have asked about, what? Circular. Find the hinge force at A. Okay, so the acceleration of the system, it is having two components, r alpha sin theta this way, and downwards the acceleration is r alpha cos theta. So now see, look at the diagram, theta, that's r, This is 2r by pi, as we know, and this is r. So this r cos theta, small r times cos theta equal to capital R. So capital R times alpha, and small r times sin theta is 2r by pi. So 2r by pi times alpha. And let's see what are the forces. The forces are downward forces mg, and for the hinge at A, let the upward force be F1 and let the sideways force be F2. Now we can apply Newton's law. So F2 is equal to mass times R alpha, and mg minus F1 equal to m times no I've sorry, this one is so m times it should be 2r by pi times alpha. Now this mg minus f1 should be m times r alpha. So therefore we can find f2 is equal to m 2r by pi, alpha is g by 2r. So this 2r and 2r will cancel. So f2 is equal to mg divided by pi. F2 horizontal force is equal to mg divided by pi. Now let's see m1. So mg minus f1 is equal to m times r times alpha. Alpha is g by 2r. So this r will cancel out. So mg by 2. So f1 equal to mg by 2. So what is the net force? So the net force at A is equal to root over of f1 square plus f2 square. So that is mg into 1 by 4 plus 1 by pi square.